All right, Spartan fans, we're going to finish up section 3.4 and look at other rates of change. So if you recall, acceleration is the derivative of velocity and velocity is the derivative of position. But there are several real world examples that involve derivatives, but don't necessarily pertain to velocity and acceleration. So we're going to look at page 130, number 10. And this is going to talk about marginal cost. So this would be a real world example using derivatives, but not necessarily projectile motion, dropping, a rock from the top of a building, etc. Okay, so it says, suppose that the dollar cost of producing X washing machines is the C of X equals 2000 plus 100X minus 0.1X squared. And we want to know the average cost of producing 100 washing machines. Okay, average is just slope. No derivatives, nothing else. So let's look at the cost of producing no machines, and let's look at the cost of producing 100 machines and go from there. And I'm using 0 to 100 because if I want to find an average, my starting, think of it as displacement, my starting cost to my ending cost. So if you plug in 0, we should get, how about 2000? And if we plug in 100, we should get 11,000 if I have done my math correctly. So our average cost is equal to 11,000 minus 2,000 all over, how about 100? Which is $90. So on average, it costs $90 to produce whatever machines these are. What are we producing? We're producing washing machines. Okay. But then it asks us, what's the marginal cost when 100 machines are produced? Okay, that's essentially asking you instantaneous. Okay, so when 100 machines are produced, it's likely not going to be $90. Okay, so this is going to be the equivalent of the derivative. By definition, that's what marginal cost means. So that's going to be 100 minus 0.2x. Right, and if I want to know 100 machines, let's plug in 100. And we should get $80 a machine. Okay, the next part says, show that the marginal cost when 100 washing machines are produced is approximately the cost of producing one more washing machine after the first 100 have been made by calculating the latter cost directly. Okay, so let's find the cost of the 101st machine. I should have labeled those other ones. Okay, so the actual cost of the 101st machine is the cost of the 101st machine minus the cost of the 100th machine. We're going to plug in. So the cost of the 101st machine is going to be 2,000 plus 100 times 101 minus 0.1, 101. Oops, that should be 101 squared. Okay, and when you plug that in and calculate it all out, you should get $11,079.90. So that's the cost of the 101st machine. Oops, let me put that up a little bit. This is the cost of the 101st machine. So the actual cost is going to be $11,079.90 minus the cost of the 100th machine, which I believe we figured out here somewhere was 11,000. Which is $79.90. So the actual cost of producing the 101st machine is $79.90, which is very close to, clearly only 10 cents less than the marginal cost of producing the 100 machines. So it actually is 10 cents cheaper if you build another machine. All right, so essentially, marginal cost is the change in the total cost equal to the change in the total cost when the quantity produced changes by 1 unit. We're going to take a look at page 130, number 16. Go ahead and sketch a graph in your notes. Let's interpret the graph before we answer any questions. Velocity. The velocity is positive. Velocity is positive from 0 to, it looks like 8 seconds. The rocket is climbing. So you might be thinking, wait a minute, this slope is negative. That means that the rocket is slowing down. So its velocity is still positive. It's just not as high as when you initially launch it. So it's launching, the velocity is really fast, fast, and it's still climbing. It's just climbing at a slower rate. What happens at 8 is that the velocity switches from being positive to negative. So right here is where the rocket starts to fall, heads back towards Earth. It's falling, it's falling, it's falling at a fast rate. And okay, right here, it is still falling. It's just not falling at a as great of a velocity as it was between whatever this is, like 8 and 11 maybe ish. Rocket is climbing, climbing, climbing. The rocket begins to fall. It's falling quickly, I guess. And then it's still falling right here. Its velocity isn't as great. Okay, so let's start to answer some of these questions. So part A says, how fast was the rocket climbing when the engine stopped? Okay, so when the engine stopped, you know what? How about we read the problem first before I just copy it all down? My apologies. When a model rocket is launched, the propellant burns for a few seconds, accelerating the rocket upward. After burnout, the rocket coasts upward for a while. That's what it's doing right here. Here is burnout. Here it's coasting. I lost my place. Then it begins to fall. A small explosive charge pops out a parachute shortly after the rocket starts downward. The parachute slows the rocket. That's what's happening right here. Here's parachute launch. It slows the rocket, so it's still falling, but not as fast, to keep it from breaking when it lands. Okay, now let's answer the question. How fast was it climbing when the engine stopped? So that to me looks like at about 2 seconds. Ish, I don't know what this 180 maybe, whatever. It's not at 100% accurate. So 180 feet per second. How many seconds did the engine burn? 2 seconds. Okay. So the rocket is accelerating upward. This is the propellant. When did the rocket reach its highest point? When did the rocket reach its highest point? The rocket is climbing, it's climbing, it's climbing, and it continues to climb until it hits the x-axis, in this case, the time axis, 8 seconds. Part D, when did the parachute pop out? Oh, we just talked about that. So it's falling, it's falling, it's falling, and the parachute pops to slow the rocket down, but it is still, so it's traveling downward. It's just not traveling as fast as a rate. So what do we say that was, 11? Does it ask you how fast? I don't know if it's asking you, but right here is, I don't know, 90 feet per second. Its speed is the absolute value of its velocity. So it's traveling at 90 feet per second. That's its speed. Yeah, how fast was it falling? It's its speed. Part E. How long did the rocket fall before the parachute opened? Okay, so here at 8 seconds, the rocket begins to fall and it's falling quickly, 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 and parachute opens right here. And so that's about 11 seconds, we said. So from 8 seconds to 11 seconds is 3 seconds. Okay, and then when was the rocket's acceleration the greatest? Okay, so if we want to know the acceleration is the greatest, it's just before the engine stopped. It's accelerating. So that looks like 2 seconds-ish. this looks linear to me. Now, okay, we're going to make some assumptions. It looks linear. So it is accelerating up, 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 up. So it's accelerating from 2 to 11 seconds. This is all linear. So it's accelerating from 2 to 11 seconds. Oops, you cannot see that. There we go. Okay, one of your homework problems, number 15, asks you to graph the derivative on your calculator. And your book was published, I don't know when, but a while ago. So it says on your calculator, it'll say graph f prime or p prime or q prime or whatever it is. And the book will say using Ender, and you're going to say, well, what the heck is that? That's the derivative key on your calculator, which in the upgraded version of the calculator before this book was published. Yeah, before this book was published. Math. And instead of Ender, it says N derivative. So when that, yeah, that's the key you should be using. And let's just do a practice in case I haven't shown you before. I'm not sure. I think I've shown you. So let's just say that you have f of x equals whatever, 2x squared minus 5x. So this is pretty basic. And using the power rule, you could find the derivative. The problem in 15 is pretty intense and you don't know how to find the derivative of it yet, but you will. So a couple ways you could do this. I recommend that you type in the function that's given to you. Whatever, what was it? 2x squared plus 5x minus 5x. So 2x squared and you don't need to worry about graphing it. So I'm actually going to turn it off so it doesn't get too confusing on my screen. Okay, so if you want to graph the derivative of this, math, number 8. Derivative of x. Sorry, let me try and autofocus this a bit better. There we go. How's that? Much better. Okay. And instead of having to type in the whole function, you can just do y1. If I can find it. How about alpha trace? Yeah, alpha trace. Okay, stop. Okay, sorry about that. Instead of typing in the whole function, you can do alpha trace y1. And so now it knows which function you want to find the derivative of. Okay, and then the key thing here is at the end, after the bar, type in x equals x. Now we already know that the derivative of this function is 4x minus 5. So it should be a line. And when you graph it, my graph has a different window. I don't know when I used it last. There it is. It's slow. It's obviously, you can see it's pretty slow, but that's how you're going to graph the derivative. So when the book says using Ender, stands for N derivative, that's what you should be doing. Okay. Let's focus that again. All right. That is the end of section 3.4.